So this is lecture number 3 and 4 of this course, Unit Process of Extraction or Principles of Extractive Metallurgy. And today's menus are like this: uh, pyrometallurgy, basis of pyrometallurgy, main mechanism behind pyrometallurgy, concept of reduction and smelting, concept of carbothermic reduction, concept of metallothermic reduction, concept carbothermic reduction versus metallothermic reduction, and examples. So basically, today's topic will be we'll be talking about basically pyrometallurgical concepts. So in the previous lecture, we have started. We have three different routes of metal extraction and metal refining, right? So we can choose any of the route to extract metal or to refine the metals. Right? And also we have discussed about what is the criteria to choose a particular metal extraction route or metal refining route. Already we have been discussing this one since earlier lecture. Fine. So today we'll focus on only pyrometallurgy. Right. So if you remember, pyrometallurgy means pyro means heat, metallurgy means extraction. So here we are extracting metals or we are refining the metals by using heat. Here application of heat will be there, right? Because we need a high temperature. So all the pyrometallurgical processes involves high temperature, where we basically take the ore to a high temperature, or during refining we take the metal to a high temperature and we do our process, right? So basically, the basis of pyrometallurgy is what? The basis behind the pyrometallurgy is the ore will be taken to elevated temperature where the ore become unstable, and once the ore become unstable, it will separate between two parts. One part is called metallic, one part is non-metallic. So basically, if during pyrometallurgy the substance are in molten form, right? Then we'll get molten metallic part, molten non-metallic part, right? So molten metallic part is basically your metal. People call hot metal sometimes, and the molten non-metallic part is called slag, right? So the slag contains all the unreduced material, all the unreduced element, right? And metallic part contains all the reduced substances, right? So you understand, suppose you are dealing with any metal oxide and it contains some impurity oxides. So what will happen? The metal oxides will get reduced to metal, and this metal will form metallic part, and the other metal oxides which are impurities, if they remain as oxides, they will join slag, but if they get reduced, they will join the metallic phase. So basically in pyrometallurgical processes, since we are dealing with high temperature, so we can get molten metals and molten slag basically. It is not always true. We sometimes get solid metal also, right? But the problem is what? If we are getting solid metal by doing pyrometallurgical process, we cannot form any kind of slag, right? So slag is the substance which contain the gangue actually, right? So the gangue cannot be removed if the metal will obtain in form of solid. So that is one of the limitation of this pyrometallurgical process if they are done at low temperature or intermediate temperature. Fine. Then main mechanism, okay, fine, let me write here. So the basis of pyrometallurgy is the ore will be taken to high temperature and it will give metallic phase, metallic phase and non-metallic phase. Non-metallic phase. Metallic and non-metallic phase. Okay, fine. So to do this pyrometallurgy process, fine. What are the requirements? What are the requirements? So first requirement is a reactor or which is nothing but a furnace. So inside the furnace, metal extraction will be done. Extraction or refining will be carried out. Similarly, we need what? We need fuel. We need fuel. So fuel provides high temperature, open combustion, right? We need flux. This will take care of gangue mineral, right? Because the ore contain gangue mineral and valuable mineral, right? Or ore mineral. So gangue part will be taken care of by flux, right? And we also need reducing agent. If you remember, in the previous lecture I told you reducing agent. Sometimes reducing agent and fuel are same. The material which behaves as a fuel will also behave as a reducing agent. So function of reducing agent is to remove the oxygen present in oxide ore, right? Or it helps in the reduction the reduction process. 5. We need external source of heat, like hot blast. Example is hot blast, because fuel need to be burned first. Then for that we need an external source of heat, like hot blast in blast furnace. So if you want to do pyrometallurgy, then you need a reactor or furnace where the reduction will carried out or refining will be carried out, right? We need a fuel, because fuel undergo combustion to provide you high temperature. We need a flux. Flux will take care of the gangue present in the ore. It helps in the removal of the gangue by forming slag. And reducing agent, because as I told, we never go to very high temperature during pyrometallurgy, because there are certain problems if we go to a very high temperature, and the process will be also expensive if we go to a very high temperature. So to carry out the process at low temperature or intermediate temperature, we do what? We use reducing agent. Reducing agent helps in the reduction process or helps in the metal extraction process. Fine. And we need an external source of heat, because fuel has to be burned first, so we need external source of heat, like hot blast in the blast furnace. Hot blast is nothing but it is a hot air or it is a hot oxygen blowing at a very high velocity into the furnace. So if you want to know the products of pyrometallurgy, what are the products of pyrometallurgy? The products of pyrometallurgy are, one is, as I told, molten metal plus molten slag, right, plus waste gas, people call sometimes flue gas, some people call top gas, plus some solid particles present in waste gas. Right. So these are the products of pyrometallurgical process. Whenever you are doing pyrometallurgy, and the condition is what? I can write molten metal or solid metal to prevent the confusion. Similarly, you have to remember, if solid metal will form, then no slag will form, right? But if molten metal will form, then molten slag will form, right? And waste gas will form. Waste gas basically like carbon dioxide, carbon monoxide. It contains some nitrogen and some other gases may be present. And solid particles present in the waste gas means some of the ore will remain in small particle form. They will carried away by this waste gas. So now main mechanism behind pyrometallurgy. So main mechanism behind pyrometallurgy is the reduction or smelting. Reduction or smelting. Right. So this reduction means everybody know what is reduction basically. In a simple way, I can write reduction means metal oxide, or metal oxide means this is ore. Fine. Suppose ore is in form of oxide. So metal oxide to metal oxide, we do reduction on it. It will gives us metal. Right. So metal oxide to metal. This is reduction. That means reduction is a process where oxygen is getting removed from the ore. Fine. In a simple way, or basically in the technical term we call addition of electron to positively charged ions or positively charged. So addition of electrons, simply you can say, that is called reduction. Right? Reduction doesn't mean, reduction is also meaning, suppose you have sulfide ore, it will become metal. Right? You have halide ore, it will become metal. Fine. So this is a reduction process simply. Metal oxide, or I can write metal sulfide or metal halide, which are ore. So your ore may be in oxide form, your ore may be in sulfide form, your ore may be in halide form. If you do reduction, they will become metal. Fine. And what is smelting now? So smelting is an operation. It's a process also, you can write, no problem. Some people call operation also, no problem. It is an operation or process, or smelting process. Smelting is an operation or process where both reduction and melting is done, right? That means if somebody is saying the ore is undergoing smelting, it means the ore is getting reduced to metal, and the metal which we'll get is in form of molten state, in the liquid state, right? So I can write ore, if undergoes smelting, it will give you molten metal, right? And obviously it will give you molten slag also, always. If simply I am saying reduction may be your smelting, or it may be normal reduction, solid state reduction, right? So if it is solid state reduction, the product will be in solid state. The metal obtained will be in solid state. There will be no formation of slag will be there, because that solid metal contains the gangue itself, or the slag itself, right? But if I'm saying smelting, that simply means molten metal will form, molten slag will form, right? that simply means also smelting is carried out at a high temperature, obviously. So there is a concept called matte smelting. So we can have two types of smelting. We can have reduction smelting or we can have matte smelting. Reduction smelting simply means there will be reduction and melting. The ore will get reduced and get melted. Fine. But matte smelting means it is also a smelting process where melting will take place, but the but the product will be not metal. The product will be molten matte plus molten slag. So matte smelting is different from reduction smelting. It gives molten matte and molten slag, but not directly metal. So it clearly means if you are doing matte smelting, you will end up with molten matte and molten slag, but not directly metal. That means molten matte is an intermediate product, obviously. From this intermediate product, we again convert it into molten metal in the later stage, right? So this kind of process, matte smelting, is carried out for certain kind of ore, certain kind of sulfide ores, basically, like copper ore. For copper ore, which is the main ore of copper, is chalcopyrite, CuFeS2, right? If you remember, this chalcopyrite is a complex ore which contains iron sulfide and copper sulfide. So to remove this iron sulfide, we have to go for this matte smelting kind of thing. Otherwise, if the ore is simple one, like iron oxide, lead oxide, or like tin oxide, we can go for directly reduction smelting. We'll directly get molten metal. But if the ore is complex, like any sulfide complex, like chalcopyrite, CuFeS2, then we have to go for matte smelting anyhow. So first step is to production of matte. The next step will be production of metal from the matte. Fine. So what is matte? If somebody will ask, what is matte exactly? What is matte? Matte is basically molten mixture, actually molten mixture of sulfides. Molten mixture of sulfides. So suppose two sulfides will be together in molten form. For example, iron sulfide plus copper sulfide together. Like mixture of, I can write iron sulfide plus copper sulfide. So during extraction of copper, we do matte smelting, where we get a molten matte, which this molten matte contains iron sulfide and copper sulfide together, right? And from this iron sulfide and copper sulfide, further we extract copper in the later stage. And it also, this molten matte also contains some metallic values also. It contains some metals, dissolved metals, right? And molten matte is having good electrical conductivity also, basically, compared to this molten metal. And another interesting point is matte smelting do not requires any kind of reducing agent. This is very interesting. This is one of the advantages. So matte smelting do not require any kind of reducing agent. But in case of reduction smelting, we always need a reducing agent, like carbon or any metal. But in matte smelting, we do not require any kind of reducing agent. Here, the sulfide itself acts as a reducing agent. Okay. So I think up to this it is clear what is the difference between reduction smelting and matte smelting, right? So what is the advantage of, what is the TVA and advantages of pyrometallurgy. Pyro over hydro and electro. So basically we understand pyrometallurgy is the main, or it is the principal route of metal extraction and metal refining. Not hydro, not electro. The question is how? How pyrometallurgy remains the principal, why pyrometallurgy remains the principal means of extraction. Right. Even if pyrometallurgy is carried out at a very high temperature, we need flux, we need fuels, right? That means we need high temperature and all, but still pyrometallurgy remains the principal means of metal extraction, not hydrometallurgy, not electrometallurgy. So there are few benefits, or there are few characteristics of pyrometallurgy that makes it the best suited process. That means in other way, I can say pyrometallurgical process is a economical process of metal extraction. Whenever we are dealing with extraction of metal in a bulk amount, right? So most of the metals which we use are extracted by pyrometallurgy, like extraction of tin, extraction of copper, extraction of iron, right? Mm, extraction of lead. Many more metals are extracted by this pyrometallurgical process, and they are extracted in a bulk amount also, right? So whenever we want to extract metals in a bulk amount, we should go for pyrometallurgy. That gives more benefit. So first advantage is it is a high temperature process. So you understand, if a process is a high temperature process, so what will happen? This is a high temperature process. So once pyrometallurgy is a high temperature process, it means the rate of reactions are very high, right? So rate of reactions are very high. So if the rate of reactions are very high, what will happen? The production rate will be high. Will be high rate of production, right? So this is the main benefit of this. Second one is we can small container, I can say reactors can be used. So small containers or reactors can be used for pyrometallurgy, because you understand, because we are dealing with ores, those are in solids, and on forming liquid, they will occupy the space of the container only, right? So small container can be used, no problem, right? Because products are in molten states. In other hand, if you look into hydrometallurgy process, big reactors, big tubes, ducts, containers will be used, right? So that is a issue with the hydrometallurgy, right? And we know that every 10-degree rise in temperature make the reaction rate double. So reaction rate becomes double due to high temperature, right? And those reactions which are not feasible at low temperature, like room temperature, are feasible at elevated temperature. That means, in other way, I can say high temperature shifts the equilibrium in forward direction. So equilibrium will be shift in forward direction, means reactant will react to give product. That means we can get metal out of the reactants of the ore, flux, and right. Low grade ore can be used sometimes, not always true. Low grade, not low grade ore, basically low grade materials can be used. Not always true, but basically you can use or cheaper raw materials. You can not low grade, better to write cheaper. It would be wrong to write cheaper grade. Cheaper grade materials can be used in pyrometallurgy process. But the main limitations of pyrometallurgy process is emissions. It leads to lot of emissions of these waste gases: carbon dioxide, carbon monoxide, nitrogen. Nitrogen is okay, but carbon dioxide, carbon monoxide, right? Some sulfur dioxide gas, right? During pyrometallurgy, and these gases are leads to global warming, right? And they also create problem like acid rain, also, right? So these are certain advantages of using pyrometallurgical process. So if somebody want to write the reaction in pyro, or how to show reactions, better reactions in pyrometallurgy. So I can write simply what ore concentrate. If you remember, it is better to write ore concentrate rather than ore or rather than mineral. So ore concentrate means it is having what ore mineral plus gangue mineral. Instead of ore mineral, we can write also metallic values. So metallic values plus gangue mineral, right? So ore concentrate ore concentrate plus, we have to use a flux. If you remember, we have to use a reducing agent, right? External heat like hot blast, if you remember, hot air or blast. It will give you finally what? It will give you metal plus slag plus waste gases. Waste gas, right? This metal may be in, as I told, solid or liquid. But here the problem is what? Slag will be always in liquid form, basically. Waste gases are basically gases. Here the ore concentrate will be in solid, flux will be in solid, and reducing agent basically also either in solid or gas form. Okay. Then external heat, that is obviously, so hot air means, suppose this is your gas, obviously. So this is the reaction showing pyrometallurgy, right? Ore plus flux plus reducing agent plus external heat will give you metal plus slag plus waste gases, right? And these waste gases also contain some solid particles. You have to remember. Now, concept of carbothermic reduction. Okay, if okay, I will explain about this pyrometallurgy again. Anyways, now yeah, I can write reduction in reduction. Sorry, I can write reduction or smelting in pyrometallurgy. Reduction or smelting in pyrometallurgy is either carried out by carbothermic reduction, carbothermic process or reduction, or by metallothermic reduction or process. Right? So these are the two means we can do reduction or smelting. So reduction or smelting can be carried out either by carbothermic process or by metallothermic process. So what exactly carbothermic process and metallothermic process is? Now the concept of carbothermic reduction. So it simply means use of carbon as a reducing agent. So carbothermic reductions are those reduction process where we are using carbon as a reducing agent. That is a simple concept. So form of carbon will be either solid carbon, that is coal, coke, like that, or it may be gas carbon, that is carbon monoxide. It is okay now. So if during smelting or reduction we are using carbon like coal or coke, or we are using carbon monoxide as a reducing agent, those are called carbothermic reduction process or carbothermic processes. Fine. The question is, why carbon now? Why carbon is one of the best reducing agent? So there are various reasons behind why carbon is one of the best reducing agent. So what is the answer? The answer is very simple. First answer is easily available. Carbon is easily available, or they are abundant in earth crust, right? Cheaper also, cheaper reducing agent. And easily available, cheaper reducing agent. Okay. So other answers are like, if thermodynamic consideration is done, carbon monoxide line cuts all the metal oxide lines in ED, in aluminum diagram. ED means aluminum diagram, right? So if thermodynamics consideration is done, carbon monoxide line cuts all the metal oxide line in aluminum diagram, right? What it means? It means the stability of carbon monoxide increases with increase in the temperature. So higher is the temperature, higher is the stability of carbon monoxide. But the stability of metal oxide, in other hand, decreases with increase in the temperature. Okay. Fine. So in one hand, the stability of metal oxide is decreasing, whereas the stability of carbon monoxide is increasing. So obviously, if in a reactor we have metal oxide plus carbon and we are applying very high temperature, then what will happen? The carbon will take away the oxygen from the metal oxide because carbon form more stable oxide. So carbon will take away oxygen from the metal oxide to form carbon monoxide, and carbon monoxide is stable, it will remain, but metal oxide will be free from oxygen and it will become metal. Okay, so this is the reduction of metal oxides by carbon in form of either carbon or in form of carbon monoxide. Basically, it has been seen that the reduction by help of carbon monoxide is good. Why? Because carbon monoxide is a gaseous phase and it can easily penetrate into the ore and it can easily take out the oxygen from the metal oxide. So because of high diffusivity of this gaseous phase carbon monoxide, it is a better reducing agent compared to direct carbon, right? So direct carbon can act as a reducing agent, or indirect carbon, which is carbon monoxide, can act as a reducing agent. So the question is, and we also know that carbon is a solid, but the moment it reacts with oxygen, it forms two volatile oxides. One is carbon dioxide, one is carbon monoxide. So you have to remember carbon monoxide is a reducing gas, but carbon dioxide is an oxidizing gas. So whenever in a reactor, both gases will be present, carbon dioxide and carbon monoxide, then always we need to find out its ratio. Carbon monoxide divided by carbon dioxide. If the ratio will be higher, that means the amount of carbon monoxide is more, then reduction will be possible. But in other hand, if the ratio between carbon monoxide and carbon dioxide is less, that means more amount of carbon dioxide is present, then reduction may not be possible or feasible because carbon dioxide is an oxidizing gas, right? And if you carefully look at the Ellingham diagram, the carbon monoxide line is moving downwards with increasing the temperature, whereas carbon dioxide line is completely parallel to the temperature axis, or it is a horizontal line. And they are intersecting at a point nearly like above 950 degrees centigrade. So that means above 950 degrees centigrade, if we have carbon and carbon dioxide, then they will react to give you carbon monoxide, right? So above 950 degrees centigrade or above 900 degrees centigrade, basically, the carbon dioxide will react with carbon, solid carbon, to give you carbon monoxide. So that is also good. That is called actually solution loss reaction. That means there is a loss of carbon in form of solution, and that solution is carbon monoxide. And this carbon monoxide is also a gaseous reducing agent. Fine. So I can write the reaction. That is also called gasification. Gasification of carbon. Here the carbon is solid, you have to remember. Gasification of carbon, where carbon is solid. So how this is happening? As I told, CO2 will react with solid carbon, right? So CO2 is your gas phase. Here solid carbon is this is solid. They will give you 2CO, right? 2 carbon, 2 oxygen, 2 CO, and this is also a gas. This is called gasification reaction. Some industry are now doing reduction by using gasification of carbon or gasification of coal. Instead of using directly coal or coke, they are using direct this carbon monoxide gas after doing gasification. And this reaction is also called solution loss reaction. Also called solution loss reaction. But you have to remember one interesting point. We cannot use carbon as a reducing agent if we are dealing with sulfide ore, because there is no analogy between carbon, sulfur and carbon monoxide, because carbon do not react with sulfur to give you carbon monoxide, right? But carbon can react with oxygen present in the oxide ore to give you carbon monoxide, right? So that's why when we are dealing with sulfide ores, basically, we convert sulfide ore into first oxide ore by the process known as roasting. So this is another topic completely, right? So after doing roasting, we are getting a oxide ore. This oxide ore will react with carbon to give you metal, right? So that is an additional process for sulfide ore, where we are first doing roasting, then we are doing reduction or smelting, right? But for oxides ore, we basically do a direct process that is called smelting or reduction, right, by using carbon. Now there is a concept called metallothermic reduction. As I told, reduction or smelting can be done by using carbothermic process or by using metallothermic. So what is metallothermic reduction? Metallothermic reduction simply means use of another reactive metal or active metal for reduction. So it simply means metallothermic reductions processes are those processes which utilize a reactive metals as a reducing agent, but not carbon. Okay. So the principle behind this is what? Principle behind this carbothermic reduction is the metal which forms more stable oxide will reduces the metal oxide. The metal which forms more stable oxide will reduces the metal oxide which forms a less stable oxide. Okay. In other way, I can write like, suppose the reaction will be M1O, M1 metal oxide plus M2 metal will give you simply M1 plus M2O, right? So it's a simple reaction you can write. So M1 is one metal, M2 is another metal, right? So the reducing agent is the M2, right? And ore is the M1, M1O, right? So this metal is more reactive, but this metal is less reactive. So this metal forms more stable oxide, this metal forms less stable oxide. So this one is used as a reducing agent. So this is the principle behind the metallothermic reduction process, right? So there is no carbon contamination. So advantage of this process is there is no carbon contamination. But in case of carbothermic reduction, sometimes there is carbon contamination. That means your metal sometimes contains carbon, dissolved carbon. Your metals maybe sometimes contains carbides. Rather than metal, it contains carbides, right? Either carbon will remain in carbide form, metal carbide form, or it may sometimes remain in dissolved form, right? Like in case of extraction of iron, we get pig iron, which contains carbon like 3.5 weight percentage to 4.5 weight percentage, or 3.5 to 4.3 or 4.2 weight percentage, right? So it is carbon contamination, right? And sometimes during extraction of some metals obtain in form of carbides rather than metal. So that is a carbon contamination. But this kind of problem do not happen in case of metallothermic reduction. So it is that means we get a very pure metal. In other way you can say. But problem will be what? Disadvantages was. So this is an advantage you can write. Advantage of this metallothermic process. But disadvantage of this process is expensive process. Obviously, we have to sacrifice another reactive metals. More is the reactivity of metals, more is the cost of that, or it is more expensive. So expensive process. So we do not prefer to do metallothermic reduction in industry. Basically, we basically prefer to do carbothermic reduction because carbon is easily available, it is cheap, right? Whereas the metal are expensive and reactive metals are more expensive, right? And we are sacrificing one metal because again it will form metal oxide. Okay. I can give an example if you want. Example in both cases. Here I can give an example. I'm writing. So what is the difference between carbothermic reduction versus metallothermic reduction? So carbothermic reduction where carbon is used as a reducing agent. Here basically reactive metals. Metal is used, right, as a reducing agent. This is less expensive process. And this is more expensive process. And you have to remember, basically metallothermic reductions are carried out in a container or in a reactor called bomb, BOMB. So where we basically take powders of metal oxides and powders of the reactive metals. We mix them together and we keep them in a bomb and we just initiate the process and the process will automatically go on, right? So we basically use powders. But here in case of carbothermic reduction, we use solids, not powders, basically. Solid iron ore, solid carbon, not in powder form. But here we are basically using powders of oxides and powders of reactive metals, which are present in a like mixture form. Right? Here carbon contamination will be there. Carbon contamination happens. That is formation of carbides, or some carbon will remain in dissolved form in the metal, molten metal. Or here what happens basically? No carbon contamination. Maximum purity. You get maximum purity. So if we want to write the if we want to write the reactions with an example, a reaction with an example, I can write like this. Example is I can write production of pig iron, that is iron, lead, tin, zinc, right? And metallothermic reductions, this is actually like example is thermite welding. So here I can write one example like, okay, it is space is available, we can write extraction of iron by carbothermic reduction process, basically smelting, for example, or you can say reduction smelting using carbon, reduction smelting using carbon. So since we want to produce iron and carbon will be acting as a reducing agent, I can write ore of iron is hematite, right? Hematite, ore of iron, plus we need a flux, right? So this hematite is basically F, okay, Fe2O3. And flux we will be using limestone or dolomite act as a flux. Okay. Dolomite and plus reducing agent and flux and fuel, right? So here reducing agent fuel are nothing but your coke and coal, powder form of coal, sometimes bulk big size coke and powder form of coal, that is called pulverized coal. Plus, you should remember hot blast, hot air. So it will give you what? It will give you iron, Fe. I can write iron. Okay. Plus slag. Suppose this is actually reduction smelting. So this will be liquid iron. And this liquid iron is also called hot metal. Some people call pig iron. And slag is also in liquid form. Plus top gas. Remember. If you remember, this waste gas, or this is also called top gas. So the top gas contains what? Carbon monoxide, carbon dioxide, carbon monoxide, carbon dioxide, nitrogen, some water vapor, plus dust particles. Right, so this complete reactions will give you the pyrometallurgical process of extraction of iron, right, from iron ore. So iron ore is hematite, which is basically Fe2O3. And if you remember, this is an ore. That means hematite will contain what? Fe2O3 plus gang. You are forgetting the main thing, gang. What are the gangs present here? Gangs is silica, SiO2 plus alumina. These are the major gang in the iron ore. Okay, so here valuable mineral or the ore mineral is Fe2O3, whereas the gang mineral is SiO2 plus Al2O3, right? Silica and alumina. So silica and alumina are the major gang in the iron ore. So we need a flux. So flux is the limestone or dolomite. Here you have to remember this limestone is CaCO3, dolomite is a combination of two carbonates, calcium carbonate and magnesium carbonates are together, CaCO3 dot MgCO3, or you can write in another way, right? So during this smelting process, the limestone or the dolomite will decompose. It will undergo calcination to give you either lime, CaO, or CaO and MgO, right? So this flux will react with this gang, SiO2 and Al2O3, right? And it will form a slag, this one. And reducing agent is your reducing agent or fuel is same, coke or coal, that is the source of carbon. It will undergo combustion to give you carbon dioxide as well as carbon monoxide, right? And carbon dioxide is the main reducing agent, and also the direct carbon. And hot blast is needed because hot blast will need to the combustion of this coke and coal, right? That is hot air or air containing air enriched with oxygen, and product will be molten iron, molten slag, molten iron. You can like iron in liquid form. I have written already liquid, slag in molten form. Then top gases. Top gases contain carbon dioxide, carbon monoxide, nitrogen, some water vapors, and dust particles. Okay. Similarly, this is one example. Another example is extraction of, or okay, let me write thermite welding. Thermite. If you remember, I told thermite welding means it is a metallothermic process or metallothermic reduction process. So what I can write? I can write aluminium. Sorry, I can write iron oxide, which may be the hematite Fe2O3 plus aluminium. Okay, so iron oxide will be in powder form, aluminium will be in powder form. They will react, the reaction will get initiated and it will give you aluminium oxide plus iron. So you can see this is the metallothermic reduction process because we are using a metal, that is aluminium, as a reducing agent. We want to reduce our iron oxide to iron, right? Is okay? So this process is called aluminothermic process. And this reaction is also called thermite welding because we can weld two steel pieces by doing this kind of reaction. This is thermite means it evolved heat. This kind of reactions evolve lot of heat energy. It is highly exothermic reactions, right? Basically, all metallothermic reductions are highly exothermic in nature. They release lot of heat, so that the products are always in form of liquid, basically. Similarly, I can write any other metal oxides, any metal oxides plus calcium. So that means here calcium will act as a reducing agent. Instead of aluminum, we are using calcium as a reducing agent. So obviously it will give you what? It will give you calcium oxide plus metal, right? This is called calciothermic. Calciothermic process or calciothermic reduction process. Similarly, we can use silicon also as a reducing agent. So metal oxide plus silicon give rise to silicon oxide dioxide, you can write. Plus metal. So this is called silicothermic process. So silicothermic reduction process. So here you can see in metallothermic reduction, we are using metal as a reducing agent, and we are using those metals or elements which form more stable oxides. So aluminium form more stable oxide. Aluminium form more stable oxide. Calcium also form more stable oxide. Silicon also form more stable oxides. So if you carefully look, these oxide lines of aluminium and calcium and silicon lies below in the aluminum diagram. That means they form more stable oxides compared to these other oxides we are using, right? Here I can also write reactions hematite plus carbon monoxide will give you magnetite plus carbon dioxide. Okay, sorry. Similarly, magnetite again react with carbon monoxide to give you woostite plus carbon dioxide. Again, what happened? Woostite reacts with carbon monoxide to give you iron plus carbon dioxide, or another reaction may happen. This oostite may react with carbon directly at high temperature. Solid carbon at high temperature will give you iron plus carbon monoxide. And other oxides, if present, other oxides, basically other oxides means gang oxides, which are gang actually, unwanted oxides. Gang oxides also gang oxides plus carbon at high temperature will give you metals plus carbon monoxide. So these are the reactions happens inside the blast furnace during extraction of iron from the hematite. So hematite first reduced to magnetite, then magnetite reduced to oostite, then oostite reduced to iron. Right. This is the sequence of reduction. Right. And there may be you can see here, carbon is a reducing agent and carbon is also a reducing agent. So this kind of reduction, this third reduction, or 1, 2, 3, first three reductions are actually indirect reduction, because instead of carbon monoxide is reacting with the ore. But if carbon will directly react with the ore or the product, then it is called direct reduction. So this kind of reduction is called of reduction called direct reduction, right? And this kind of reduction, first three kind of reduction, is called indirect reduction. So this is actually solid carbon. This is solid carbon. I can write solid directly if you have any confusion. Solid. And these are actually gas, right? Okay. And these are solids, obviously. The ore will be in solid form. And the oostite is solid, and sometimes the oostite may be liquid because of high temperature. So I think up to this it is clear. Shall I stop the recording?
Yes, sir. Yes, sir.